Hello everyone and welcome back. Now, in the past few videos, I've spent a lot of time talking about solutions to differential equations. And of course, rightly so, that's sort of the purpose of this course. But, as I have said before, when it comes to differential equations, most of the ones that you encounter in the wild just can't be solved, no matter how hard we try. So the question is, what can we do? Again, I study differential equations, and I can't solve a lot of the ones that I work with on a day-to-day basis. Does that mean I do nothing all day? Of course not, right? We have workarounds for how to understand these things from a qualitative perspective. And that's what we're going to focus on in this lecture. So, if you think back all the way to the first lecture, I introduced slope or direction fields. And that was a geometric way of getting a feel based on calculus of how a differential equation behaves, and in particular, what happens to their solutions or what they do. Now, what I'm going to introduce is actually what I think is a slightly easier version of that, and that is going to be for a phase line diagram. Now, phase line diagrams are particular to first order scalar, or just one independent variable, autonomous differential equations. Now, what does it mean for a differential equation to be autonomous? It means that I can write it like this. There's no explicit dependence on the right-hand side for the independent variables. So it might be t or x. I know I kind of move them around at will, but that's just to sort of get you fluent with them. But if you think about what we did with the saltwater tank or the falling object, those were both autonomous equations. Autonomous equations come up all the time, right? Things that don't explicitly depend on when you look at them and when you measure them, right? So we are going to talk about these autonomous equations today, and in particular, how we can analyze them. And we're going to do this in an example-driven context. Okay, so what I want to do, I want to look at the so-called logistic differential equation. Now, this is one of the most famous ordinary differential equations in all of math. It sort of serves as a prototype for understanding nonlinear systems. If you really wanted to, you could sit down and you could solve that thing. It's a separable equation. In fact, all autonomous systems are separable. Just divide off all the y terms, integrate up. You might have to use a little bit of partial fractions to solve it, but you could. But I don't want to, right? I don't want to have to do partial fractions. There's got to be a better way to understand what happens here. Okay, so just a little bit of context first. This differential equation is typically used as a rough or introductory model to describe populations of animals. Now, y in this case represents the percentage of animals in an environment relative to their carrying capacity. So in fact, this one value here represents 100% of the population at the carrying capacity. That is how much the environment can sustain. So for example, maybe only 10 people can live in a room or something like that, or whatever this means. Or maybe, you know, your fenced-in enclosure can hold 100 sheep. After that, you just can't feed them, right? So that's just at carrying capacity for 100 sheep. My value r here represents the birth rate, so it's going to be positive. And the first thing that we can do when we look at these autonomous equations, the first thing you should always do is look at what the equilibria are. So the equilibria in this case, well, I was nice and I gave this to you in a factored form, so you don't have to think too hard. But I have two equilibria, one at 0 and one at 1. Now again, in the context of an animal population, what do these things represent? 0 represents 0% of the population. That is extinction. So whatever that animal population is, it doesn't exist, right? This would be our unicorns or something like that. They never had the chance to exist. Similarly, at y equal to 1, this means you're at 100% of the carrying capacity. You're occupying all of the space and all of the resources here. And so everything, you know, you've got 100 sheep in your pen and everything is sort of staying level. There's no room for births. There's no room to take anybody out because they'll just be replaced by a birth right away. Okay, so the question is, what can we do with the rest of the equation, right? The equilibrium solutions are just two particular solutions to a much larger differential equation. Well, here's where calculus comes in. Remember, this is the derivative, and it is describing the rate of change of your solution to your differential equation. Again, this thing is polynomial. We can apply the theorems from the previous lecture. We know that unique solutions exist. Question is just what they do. Well, solution by definition is a function that actually satisfies this when I plug it in, and that tells me that my derivative is equal to whatever I'm doing in the function at that time. Okay, great, Jason. It kind of just feels like you just spoke in circles there, right? Does that give me any information that I care about? Well, I would like to think the answer to that is yes. First of all, when you have a positive derivative, your function is increasing, right? That's just the definition. Then so when is this thing positive, right? When is my derivative positive? It's when this function on the right-hand side is positive, which is when 0 is less than y, which is less than 1. How did I get that? Well, no magic. All I did was just sketch out that function, right? So that function is just a simple little one-hump function. It has two roots. Those are my equilibrium values. And so here's where I'm positive. So this is y, and this is ry times 1 minus y. All right, so I never had to tell you what the value of r is. It's going to work for any positive r. But what I do know is that for any positive r between 0 and 1, my function is increasing. Similarly, my solution will be decreasing if I am either less than 0 or bigger than 1. Okay, so how does that actually help me, right? Does that tell me anything that is useful in here? Well, I would say yes. So what you get, or what you can do, is you can draw a phase line diagram. So the first thing you do, it's a line diagram, so I'm going to draw a line. And I will put in my two equilibriums, or my equilibria. So I'm going to put 1 here. I'm going to put 0 here. These are my two equilibria. This is just on the number line. And what I know is that if I'm between these equilibria, then I am increasing. Now, I am increasing the value of y. I am moving to the right on the number line, right? We know that when we move to the right on the number line, numbers get bigger. So here's what we do. We indicate that with arrows. The arrows tell us that we are increasing when we are between 0 and 1. Similarly, when I am less than 0, I am decreasing. And when I am bigger than 1, I am decreasing. Remember, decreasing is moving to the left on the number line. That right there is a phase line diagram. That tells me everything I need to know about this differential equation. So the question is how? How does that tell me everything I need to know? First of all, it tells me the equilibrium values. I've got them clearly indicated for myself here at 0 and 1. And it tells me how every single other solution to this equation behaves. So imagine, just for exposition, I took an initial condition right down here. So I had initially some small population. Maybe I had, like 5 rabbits or something like that, right? And I have an environment that can support maybe 100 rabbits. Okay, well, that gives me essentially 5%, right, in terms of this equation, of the environment is being occupied by rabbits. Then I know that the rabbit population is increasing here, right? Because I'm between extinction and the carrying capacity. But, so I move up a little bit, right? So I move a little bit to the right, maybe. But now I sort of reevaluate. Again, I'm still between 0 and the carrying capacity. I'm still increasing my population, so I'm still going up. Well, now I'm still between the extinction and carrying capacity. I'm still going up, still going up, still going up, still going up, until eventually, as time goes to infinity, I am going to converge to the carrying capacity. That's what this thing is telling you, right? You imagine these are sort of like arrows in a video game that they're pulling you in a certain direction. It's telling you that if you start between 0 and 1, as time goes to infinity, you will converge to 1. Same thing out here. If you start above your carrying capacity, you have 110% of the animals in this pen just can't support it, right? They start dying off, and they start dying off in a way that you converge back into the carrying capacity, right? All you can support is 100%, 1. Now, if you start below 0, this doesn't really mean anything in the physical context here because there's no such thing as a sort of negative population of animals. But we can just talk about it for a second. If I start below this, well, all I'm going to do is run off. And in this case, there's nothing to catch me. There's no more equilibria. So I'm going all the way to minus infinity here, right? So this is sort of why we don't include this in the differential equation, because it means nothing in terms of a population of animals, and it just goes all the way to minus infinity. There's nothing to catch you anymore. But that tells me everything I need to know about my differential equation without ever once solving it. If you wanted to, go ahead, solve it, have at it. All right? You'll have all the fun in the world, but I got all the information in a much easier way. Now, in this case, we refer to the equilibrium 1 as being stable. Now, why did I call that stable? Well, think about what happens. If I start a little bit off of the carrying capacity, maybe I start at 105% or I start at 95%. Either one, what happens? I converge back into that stable equilibrium. So that means that I got a little bit of error, right? Even if I'm off by a little bit, I'm always going to go back to the equilibrium. The way you should think about stable equilibrium is a ball rolling into a gutter, into a ditch, okay? So if I place the ball at the very bottom of the ditch, it's not going to move. It's in a state of equilibrium. There's no forces acting on it. Now, if I take the ball and I move it up the side of the ditch, what's going to happen? Well, it's not at equilibrium. It's a little off, but it's going to fall and roll back into that equilibrium state. That's what we call a stable equilibrium. All right? It allows for a little bit of error. Okay, well then we call, in this case, 0 the unstable equilibrium in this case. Why is it unstable? Because every little mistake you make is going to be fatal. No matter how close you start to extinction here, you will never go into extinction. You will always be pushed away from it, okay? So if you start with even, 0.000001% of the population at carrying capacity, you are going to grow and grow and grow and grow and grow until you reach carrying capacity. The way you can think about an unstable equilibrium is if you think maybe a broomstick, for example. You try and balance a ball on the top of a broomstick. Now, physics tells us that there is actually a balance point on the top of that thing. It can be done. But maybe pause the video and try and do it yourself, right? It's not going to work, right? You're going to keep falling off in some direction. That means that no matter how close you are to that perfect equilibrium, any little minute hair or little piece of dust that throws you off has fatal consequences. You fall off the top of the broom. Same thing here. Any little minute change from 0 has fatal consequences. You will move away from 0, no matter what. You will say goodbye to that equilibrium, and you will run as far away from it as you can. So that's how you can think about stable and unstable, right? One allows for error, the other one doesn't. Let me guide you through one more example here while we're talking about these autonomous equations, and let's augment our example to a slightly more realistic example. So let's again use R. This is going to be a birth rate. This autonomous equation is going to represent a species. And again, it's going to be the population of the species, the percentage as according to the carrying capacity. So we can see the 1 minus y term in here again. Same as the logistic equation. 1 is 100% of the population. We see very, very similar terms. The only thing that's different is this right here. Now in this case, alpha is going to be between 0 and 1. The solution or the results are going to hold for every single alpha here, as long as it's between 0 and 1. And this is sometimes called a threshold parameter or an allele parameter. And this equation is describing what's called an allele effect. So let me solve the equation, then let's talk about what it means in terms of a biological population. So again, let's talk about the equilibria. Same thing. Luckily for you, I gave you the equation completely factored. So one equilibrium is 0, another one is alpha, and another one is 1. So extinction, then full carrying capacity, and then this thing alpha in the middle that we haven't really discussed yet. Okay, let's draw the phase line diagram. Right? Remember, nothing really too fancy has to go on here. Start with my equilibria. Okay, so I've got 3 equilibria. I kind of drew them a little too big, but it's really just to sort of exaggerate what's going on here. If I sketch out this cubic equation, this minus here means it's pointing downwards. So that cubic is going to look like a sort of S on its side, which is going to minus infinity as y goes to infinity. So that means that it is negative beyond 1. It is positive between alpha and 1, right? So that's the piece that comes up. It is negative between alpha and 0. And it is positive below 0. Okay, so if you need to, throw that into something like Wolfram or Maple or Mathematica, sketch it out so then you can see and make sure that my positive and negative regions correspond to the ones that you get from that sketch. But what does this say? If we look at my logistic phase line, it said basically everybody is going to move to carrying capacity. But here now, we see that there's something that separates out who lives and who dies. Alpha here is our threshold. If your population is too small, if it's between 0 and alpha, then you are going to go extinct. But if your population is above that cutoff threshold alpha, then your population will survive and it will go to carrying capacity. Right? So the way you can interpret this in terms of a biological model is that you do, between 0 and alpha, you just don't have enough of your population to reproduce and to continue to sustain itself. It's just a population decline into extinction. But if you're above this threshold alpha, then you have enough of your population to reproduce and sustain a healthy population to go up to the carrying capacity of the environment. Now, not much changed in terms of my my carrying capacity here. This thing is still stable, right? I still have all my arrows pointing into it. But now something weird happened, and technically my extinction is stable as well. All the arrows are pointing into it nearby, right? So it's giving me a little room for fudging here. And these things are now separated by an unstable, sometimes we call this a separatrix state, alpha. Tells you, whatever side of alpha you're on, tells you if you live or die. Now, just for the fun of exposition here, let's ask ourselves what happens if we sort of change the value of alpha. Right? So I said that this is for all alpha between 0 and 1. What if instead I took alpha less than 0? Okay, so I'm not going to sit here and tell you that this means anything from a biological standpoint. I just want you to think about this from a mathematical standpoint. I want you to see what happens here. Okay, again, my equation is fully factored. Equation didn't change. I just moved where the equilibrium is. So I still have 3 equilibria. I have 1. Now I have 0. and now I have alpha over here. Right? Similarly, I still have that same sort of standard S shape, and so I still get that beyond 1 I'm moving to the left. Between 0 and 1, I'm moving to the right. Between alpha and 0, I'm moving to the left. And below alpha, I'm moving to the right. Okay, so what really changed? Honestly, not a whole lot, right? If you cover up my labels, looks like exactly the same thing. Stable, unstable, and stable. But once you start labeling, that's when things get funky. Because think about this. Originally, in the original equation up here that displayed this thresholding, the extinction state was stable. Now the extinction state is unstable. This piece right here looks a whole lot like my logistic function from the previous example. But now, similarly, my threshold state, alpha, became stable. So what happened here? If you can play this movie in your mind, think about alpha being between 0 and 1 and decreasing it down below 0 to get from here. So I'm playing a movie starting from here and getting from here. This is my extinction state. This is my alpha state. It decreases until alpha equal to 0 when they hit each other. And then alpha keeps going below until you get to this phase line diagram. Now what happened? When they collided, they exchanged stability, right? An unstable state, alpha, hits a stable state 0. And once they collide, alpha takes the stability and 0 is left with the instability, right? It's sort of like a handoff here that's happening. You can also ask yourself what happens at the edge case, right? What happens when alpha is equal to 0, right? In this case, two of my equilibria are exactly the same. So I've only got 2 equilibrium values. I've got 1 at 1 again. This one never changed. Nothing changed here. And then I've got 1 at 0, which is a double root of my equation now. Sort of a double root of my equilibrium, a double equilibrium almost. Again, draw the arrows on here. This one's a little ugly. And what happened now? Well, the nice thing is nothing really has been happening to my carrying capacity state, right? So 1 always remains stable. But now look at 0. It's not unstable because not everything is flowing away, right? If I look to the left, we're not all flowing away. But it's not stable either because not everything is flowing into it. So it's sort of somewhere in between, right? Something strange is happening. And the reason something strange is happening is because it's in between these two exchange of stability states, right? Up here, remember I said that I have stable and unstable from 0 and alpha, and then when you decrease alpha across 0, they switch that stability. The place where the switching happens is where you get really, really weird stuff happening. Sometimes we call this a metastable state. Very, very strange thing that's happening because it's sort of stable on one side and unstable on the other side. And really what you're looking at is essentially a sort of logistic equation as long as you're looking from 0 to infinity, right? Again, if you're looking at a biological population, then you're essentially just getting a logistic equation. Everybody goes and reproduces until they can't anymore. Okay, so one last thing in regards to this. You can do the same thing if alpha goes above 1. What's going to happen now is that the exchange of stability is going to take place with that y equal to 1 state, the carrying capacity state. Again, the same thing. Alpha is going to run right through it, steal its stability, and leave it unstable. So I'm going to leave that for you. Try it out. Have some fun. Write that down. Make some phase line diagrams, right? They're fun. They're relatively easy. It's a nice, light way of trying to understand qualitatively what's going on with these differential equations, right? Of course, I didn't get a solution. That's okay, right? If I wanted to get a solution to either one of these equations, I've got to use the method of partial fractions if I'm going to apply separation of variables or make these, or look at these as separable differential equations. Personally, method of partial fractions is very complicated for me. I find it not to be the easiest thing in the whole world to do. You know what is pretty easy? Making these little sketches. And now I have a pretty good idea of what's going on without actually having to, write down some integrals and do all kinds of complicated work. Really, we didn't even really use calculus for this, other than understanding what a derivative is. All we had to do was sketch out functions. And I am willing to bet that's something you can handle. That's something that you're probably pretty comfortable with. So hopefully you like this method of phase line diagrams as much as I do. Okay, I'll see you in the next lecture.